This is our ECE 178 final project. We created an integrated FPGA alarm system simulation.
My name is Zuniga-Ramirez.
And my name is Keith Johnson. This is an overview of the state machine that governs our embedded system. It consists of two FPGAs, the control unit and the alarm unit. The control unit modifies the overall state of the system. It relies on the user entering a password to advance the system state. At startup, the system is in the alarm inactive state. When the user successfully enters their password, the system proceeds to the alarm active state. From here, the alarm FPGA uses the distance sensor to detect any nearby objects. The alarm is a two-level security system whereby the first level indicates a warning and the second level indicates danger. The warning state is triggered when an object is within a medium range, while the danger state is triggered when an object is within close range. Once the danger state is reached, the alarm will sound until the user enters the password. Furthermore, at any of these states, the control FPGA can deactivate the alarm if the user enters the password. The overall system is described here. Both FPGAs, the alarm FPGA and the control FPGA, use the Nios 2 processor. The alarm FPGA features parallel input-output PIO cores implemented as GPIO, 7-segment displays, and LEDs. The control FPGA contains JTAG UART, an SD card interface, and GPIO. The GPIO of the control FPGA sends the system state information to the alarm FPGA. To create the system and its peripheral cores were created using QSys. With the proper inter-system connections, simple and complex systems alike can be generated in this software. A Quartus IP or QIP file will be generated, which may then be imported into a Quartus 2 top-level Verilog module. Next, we need to instantiate the system. A top-level Verilog module is created to specify the ports and module connections of a system. Additionally, this module imports and instantiates the QSys system. By assigning valid pin names to specific ports, pin assignment corresponding to the FPGA can be performed. To implement the system, we can use Altera Monitor program, and the system generated in QSys and compiled in Quartus 2 may be downloaded onto an FPGA. Once downloaded, the system may be programmed with either assembly or C code. The JTAG UART core is of primary importance for the control FPGA. It allows for direct communication between the FPGA and a host PC. Using a terminal application, ASCII characters can be typed into a keyboard and directly sent to the FPGA's UART buffer and vice versa. The JTAG UART core is used to allow the user to attempt to enter their password with the host PC keyboard. The SD card interface allows for reading and writing of 512-byte sectors. The attempted password entered into the terminal is saved to the SD card and is then compared with the actual password. If correct, the system advances to the next state. The SD card is pre-written with status messages at different sectors in the form of ASCII characters. For any given system state, a message associated with that state is retrieved from the SD card and displayed on the host PC terminal through the JTAG UART.
The alarm components are 2 FPGAs, a distance sensor, 3 indicator LEDs, a speaker, and a distance proximity indicator. The 2 FPGAs used in this project are the D2115 boards by Altera. One was used as the control unit and the other one as the alarm unit. The distance sensor must keep track of the distance between the sensor and an object. And also, the distance must be displayed on the FPGA hex display. The 3 indicator LEDs are the alarm status LED, warning state LED, and danger state LED. The alarm status LED must indicate whether the alarm is active or inactive. If the alarm is active, the LED must be on. Otherwise, it must be off. The warning state LED must indicate if an object is within the range of the warning state. If an object is within the warning state range, the LED must be on. If the object moves out of the warning state range, the LED must turn off. The danger state LED must indicate if an object has entered the danger state. Once an object enters the danger state, the LED must start flashing and remain flashing until the alarm is deactivated by the control unit. The speaker must be beeping while an object is within the warning state range. If the object enters the danger state, the speaker must start ringing and it will not turn off until the control unit deactivates the alarm. The proximity distance indicator is the FPGA onboard LEDs. As the distance between the object and the sensor gets smaller, the LEDs must start lighting from right to left to indicate the proximity of the object. The distance sensor used in this project is the ultrasonic distance sensor HC-SR04. To start measuring, the sensor must receive a trigger signal. The trigger signal must be high for at least 10 microseconds. This will make the sensor to transmit 8 cycles of ultrasonic waves at 40 kHz, and then the sensor will wait for the reflected ultrasonic signal. If an object is present within the working range of the sensor will set an output high signal, also known as the echo signal, and delay this signal in the high state to indicate how much time it took the wave to travel back and forward. To obtain the distance, the echo time must be divided by 2 and then multiplied by the speed of sound. The alarm FPGA was programmed to send a trigger signal to the sensor through a GPIO pin. The trigger signal was sent every 200 milliseconds. In order to obtain the distance, 2 Verilog modules had to be created. The first module is the echo detector module. The purpose of this module is to detect the echo time. The input to the module is the echo signal coming from the sensor. Once the echo detector module is done calculating the echo time, it sends the echo time and a done signal to the second Verilog module. The second Verilog module is the distance calculator module, which takes care of calculating the distance. After the distance is calculated, it is sent to the alarm FPGA, which is programmed to make decisions based on the measured distance. Each of the 3 indicator LEDs are connected to a GPIO pin of the alarm FPGA. In order to establish an interface between the system and the speaker, a Verilog module was also created. The purpose of this module is to generate the required speaker sound. The input to this module is a signal coming from the alarm FPGA, which determines what kind of sound needs to be played by the speaker, whether it's a beep or a ring. The output of this module is an oscillator signal, which produces the sound specified by the FPGA. The speaker interfaces with the module through a GPIO pin of the FPGA. Now it's time for a live demonstration. So here, this is the alarm unit. This here is the sensor, and these 3 LEDs here are the indicator LEDs. The yellow LED is the alarm state LED. If the alarm is active, this LED will remain on. If the alarm is inactive, the LED will remain off. The blue LED is the warning state LED. If the object is within the range of the warning state, the LED will light. If the object leaves the warning state range, the LEDs will turn off. And the red LED is the danger LED. This LED will start flashing once the object has reached the danger state. This LED will remain on until the control unit disables the alarm. This here is the speaker. The speaker will start beeping if the object is within the warning zone.
Same as the warning LEDs, if the object enters the danger zone, the speaker will start ringing and will not turn off until the control unit disables the alarm. The onboard LEDs are the proximity distance sensor. As the distance gets smaller, the LEDs will start lighting from left to right. The green LEDs indicate the warning state. Once the red LEDs start lighting, it means that the object has reached the danger state. The alarm also displays the distance on the hex display. As the object gets closer to the sensor, the distance decreases on the hex. On the other hand, as the object moves away from the sensor, the distance increases on the hex.
This is the control FPGA. It controls what state the system is in at any point in time. It specifies to the alarm system what state it's in using this GPIO line. If it's inactive, a 0 is sent over this line. If it's active, a 1 is sent over this line. The two primary components besides the GPIO of the control FPGA are the SD card. This card stores the status messages, which are displayed to the JTAG UART, as well as the password that the user must enter to set or unset the alarm. The JTAG UART is displayed here, and the messages saved within the SD card are displayed here. The first message that comes up is the inactive state. So now we'll give a demonstration of the working alarm system by typing in the password. So the alarm starts off in the inactive state. To activate the alarm, we need to type in our password, which is ECE178 project. So now the alarm is active. To put it in the warning state, the object must be brought into a reasonably close distance. To take it out of the warning state, we need only remove it from that distance. And to take it to the danger state, we need to bring it in close proximity. And the only way to get out of the danger state is to type in the password. And you can see also that once the object is removed, it still rings the alarm. So to take it out of the running state, we need only type in the password once again. And you can see that the alarm has been deactivated. This concludes our project for ECE178.